good afternoon, and my name is Lucy Powell, and it's my honor to introduce the seminar today. So this is an ECPE seminar, and this particular seminar is jointly sponsored by Rasei, the Renewable and Sustainable Energy Institute, which is a joint institute between the National Renewable Energy Laboratory and CU Boulder. And our speaker today is Dr. Brian Johnson of the National Renewable Energy Laboratory. So Dr. Johnson received his bachelor's degree in physics from Texas State University in San Marcos, and then he went on to earn his master's and PhD in electrical computer engineering at the University of Illinois Urbana-Champaign. He finished his PhD around February of this year. I met him at Urbana-Champaign in February, and he started at NREL this March.
Yep.
And so, while a graduate student, he received a number of fellowships, among them National Science Foundation Graduate Research Fellowship. His research interests are in renewable energy systems, power electronics, and control systems. And I think we're going to hear about all those topics today in a seminar on this talk on virtual oscillator control of voltage source inverters. So join me in welcoming Brian Johnson.
Thanks, everyone. So, as Lucy indicated, I just graduated this past spring from University of Illinois and just joined the National Renewable Energy Lab. So I've been in the area just for about 8 months or so. I haven't skied before, so anyway, the topic that I'll be discussing today is mainly focused on some work I did during my PhD work. In addition, I've been keeping up with it and adding extensions to this topic. So some of these are one of the topics I did back at Illinois and are still working on now. So before I go ahead, I just wanted to acknowledge the collaborators I have listed on the bottom here. So each of these people has contributed in some unique way to the research I'm presenting, so I thought I'd mention them. So as the title of the slides indicate, I'm going to be talking about this concept we like to call virtual oscillator control. And actually, so before I go ahead and continue, I was told that there's a potential that the audience members may be interdisciplinary. So I was just wondering if anyone who's not an electrical engineer, if you could raise your hand. Okay, there you go. Just so I wanted to make sure there were no paleontologists in the crowd or something, explain some of these concepts a little more. Yeah, so I guess in the interest of time, I'll go ahead and jump into it. So what I wanted to start out with is to kind of just point out just how incredible it is that we have this huge and expansive power system that interconnects these really geographically sparse areas. But if you think about it, it's all an interconnected system, or actually just large regions of it. And one interesting aspect of this is that this really large-scale system maintains stability and synchrony. So that means that if you were to probe the voltages at very large separated distances between different points, you would actually see that the entire system is swinging together at 60 hertz. And so it's just amazing for me to think about something like that. So the power system is conventionally driven by dynamics of huge, large synchronous generators. So these are usually fed by turbines, from boiling water. So these are coal-fired power plants or nuclear power plants, for instance. So one really interesting aspect of the power system is that it kind of came about organically. So a long time ago, when they started interconnecting all these generators, there was no well-defined plan that we're just gonna make this huge expansive system that stretches 1,000 miles at least from one end to the other. So it just kind of came about, and having a complete understanding of what gives rise to stability and synchronization in this huge interconnected system is still not completely understood. So people have been studying this for several decades. And usually a lot of the mathematics of trying to understand the properties are based on making a lot of simplifications, because it turns out that the full-blown dynamics of even just a single generator is nonlinear, and there's a lot of differential equations in just that one generator. So you can imagine that looking at a large-scale system, the problem becomes very difficult to solve. So what we're going to be discussing today is actually something a bit different, something that's smaller scale, something that's a bit more tangible in a sense. So we're going to be talking about systems that are commonly referred to as microgrids. So generally a microgrid refers to some sort of small-scale power system that has controllable energy resources on it. So this could be generation such as PV or storage such as batteries, or fuel cells, for instance. And sometimes these microgrids can also have controllable loads, so you can have a demand response on the system. So there's all sorts of interesting aspects to study with respect to microgrids. Now, one of the driving aspects of microgrids is that the idea is that if you're going to distribute all of these energy resources down to the distribution level of the grid, so at smaller scales, then you can utilize the presence of these energy sources and storage and controllable loads to enhance reliability. So what that means is that, let's say that something bad were to happen on the large-scale power grid, you could separate the microgrid and maintain uninterruptible power to your local loads. So whenever you do that, that is called an islanded system. Now, one of the things about these systems when they're islanded is that you have to deal with controlling these inverters so that the system maintains stability, because we're no longer going to be connected to the grid potentially. So you have to be able to provide this self-synchronizing capability power system itself gives rise to. And unlike the conventional power system, which is based on electromechanical dynamics and large generators, you can imagine that if we're introducing all these DC-type energy sources, we need power electronics to interface everything. So no longer are we looking at systems that have large rotating inertias. So we need to figure out a way to control these inverters to give rise to the results that we're looking for, namely a system that oscillates at the desired frequency while maintaining the voltage for the loads. And also, you would like to do this without any explicit communication. So it's a bit more complicated if you were to have a communication network that was literally keeping everything synchronized. So we would like for this to just give rise naturally through the interactions of all of these units together. So whenever it comes to controlling islanded microgrids, which is what I'm going to be focusing on today, and maintaining stability and synchronization, which is pretty much the main name in the game, is a method called droop control. So this has been around since the early 90s, and basically the premise of droop control is that you digitally control each inverter such that to a first approximation, it behaves like a system of interconnected generators. And so you can imagine that given that the conventional power system is built up from a large collection of interconnected generators, this is a natural solution that people have converged onto. But we're going to be looking at something that's a bit different, and in an attempt to kind of highlight the concept that we're going to use for this, I have a short video here. So we're going to be using the concept of coupled oscillators to design the controls for the inverters. And so here is a really neat, just kind of simple video of a system of metronomes. So one way to think about it is that, or actually let me just explain a little bit what's going on. So it could be mutually or not synchronized, obviously. And by putting them on this platform so that they can interact with each other, synchronization just emerges from the system. So if you were to study this kind of system, it's actually a coupled oscillator system. So in this case, the coupling is due to the mechanical forces between the metronomes on the system. So in that same spirit, we're going to be doing something very similar, but with power electronic inverters, where you could think of each inverter as essentially behaving like one of those metronomes, and maybe that platform that gives rise to the coupling is representing the electrical network in the microgrid that interconnects everything. So the next part of the talk here, I'm going to be introducing our method and to give a description of just how it works. So again, it's called, we like to call it virtual oscillator control, and as the name implies, what we're going to do is we're going to digitally program each inverter so that it emulates a nonlinear oscillator circuit, which is, here's the nonlinear oscillator that we're going to be using as the basis for the control. And so essentially what we do is we just measure the variables at the output terminals, and then we process those into a digital controller where we're emulating the circuit. And then the variables of this circuit we're emulating are used to control the switches on the power electronics. And so because this oscillator circuit forms the foundation of our controller, I wanted to give everyone here an intuitive sense of exactly what this little oscillator circuit is. So at some point, most of us have seen just the straight harmonic oscillator, which is an LC circuit. So this has a resonant frequency, which is given here. And as long as the initial conditions are non-zero, then there will be a self-sustaining oscillation that will continue forever. And the amplitude of the oscillation is dependent on the initial conditions. So that's pretty basic. So you can imagine that if you were to augment this with some sort of dissipative element, then the oscillation will just die away. So what we want is to have an oscillator circuit that has a level of predictability so that despite any initial condition, it will converge to an oscillation with a fixed amplitude that we can control. And also we want to be able to tune the frequency of that. So what we're going to do is take that RLC circuit and add a nonlinear voltage-dependent current source. So this little symbol here is the y-axis is denoting the current consumed by this block, and the x-axis is the voltage across it. And so you can see it's a nonlinear function. And I just wanted to first point out some of the structure of the circuit because we're going to be building on some of these concepts later in the talk. So there is a linear subsystem, which is the RLC circuit here. And so from here forward, I'm going to be denoting the impedance of that parallel RLC circuit is ZOSC. And then also in later slides, this nonlinear part, I'm going to just denote with a little a diamond current source symbol instead of drawing out the piecewise linear function every time. So whenever it comes to design, we can get the desired frequency by tuning the resonant frequency of it. And some of these other parameters, we can tune those to get a desired amplitude. And another thing I should point out here too is, and this is important for the analytical side of things, for the slope of this nonlinear function here, we just require that it has a finite value. So we designed this particular nonlinearity such that the absolute value of the slope is always denoted by a sigma here. So then I'll show you what I mean by it has this self-sustaining and predictable behavior. So let's say that we've tuned this and all the parameters so that we have, let's say, a 60 hertz oscillation at 1 volt. So as long as you have any non-zero initial condition, it will converge to that same limit cycle or oscillation at 1 volt. So here there's some small initial condition, and you can see that it swells until it rises to the prescribed value that we want to. And so intuitively, what's happening is that this nonlinear element, when the oscillation amplitude is small, it actually acts like an energy source. So it's dumping energy into this resonant circuit so that it's pumping up the size of the oscillation. On the other hand, if we start out with some large oscillation, this actually starts acting more like a damping or a dissipated element. So then it will damp out large oscillations. So if you kind of extrapolate that large oscillations get damped and small ones get pumped up in size, you can see that there is a unique amplitude that it will converge to, as long as you have non-zero initial conditions. And so you can actually prove that it will always converge to this exact amplitude and frequency using something called Leonard's theorem. So then, whenever it comes to hardware implementation, that's what I'm showing here. So what you can think of is that this bottom part of the diagram is the power electronics. So this is the inverter that performs the DC to AC energy conversion. This is some filter impedance. And then this is just a measurement. And then this connects to the rest of the microgrid. Now on the digital side of things, what we're doing is we're essentially just taking the second order nonlinear differential equation corresponding to this oscillator circuit, we're discretizing it, and then we're just programming it into a microcontroller. So one way to think about it is that this oscillator doesn't physically exist. It's just no more than a few lines of code on a microcontroller. And we're interfacing this fictitious oscillator to the real world by taking our measurements, which are shown here, and processing them through an A to D converter and extracting the measured current through this fictitious oscillator. And the whole point of doing this is that the inverter, which is the power electronics here, actually will follow the dynamics of the oscillator that we're emulating inside of the controller. So another way to look at it is that the average voltage at the output of the inverter, if you average out and neglect switching, it actually follows this voltage that the oscillator is generating. And so the whole reason we're doing this is because it turns out that if you take a system of inverters and control them with the virtual oscillator control, which I'm denoting as VOC, this system of this power electronic system on the left will actually behave like the system with interconnected oscillators on the right. And the whole reason we're doing this is because it turns out that there are some really wonderful properties of whenever you interconnect these oscillators into an electrical network. Namely, they synchronize at the same frequency and they share the load current. And this is entirely done without communication. It's just due to the electrical coupling between the oscillators. Or another way to think about it is that the fictitious oscillators, which are inside the controllers, are actually coupled to each other through the real physical network. So that's a really neat idea, I think. And so if you were to compare virtual oscillator control and Droop, one way to think about it is that virtual oscillator control is actually acting on instantaneous measurements. So you can think about it as it will stabilize despite what the waveforms are looking like on the system. It's acting on a more instantaneous level. However, on Droop control is actually based on a heuristic or a relationship between power and frequency and voltage and reactive power. And that's a steady state relationship. And you use that steady state relationship to formulate a control law in Droop control. And because in Droop control you're actually measuring real power and reactive power, and you're trying to assess what the steady state value of those are, then you could think of as Droop control is acting on a sinusoidal steady state of that system, and it makes it a bit slower sometimes. So the next part of the talk is going to be focused on the mathematics behind this. So the short story of this is that whenever we stumbled on this idea and I was simulating it, it just worked. And it left us scratching our head, and the big question was, why does it work? And so there was a considerable amount of effort on the mathematical side of things to try and figure out just why does this system of oscillators synchronize? And just to give you a little bit of background, most of the previous work related to coupled oscillators is in the systems biology area. So in those types of systems, they don't look at systems or networks that have loads that are consuming power. So we had to make some adjustments and adapt some of the theory from other fields. So this part of the talk here is partly to answer the question of why, and then also what we want to do is we wanted to have a clear mathematical description or understanding of when inverters will and will not synchronize with this type of control. And that's incredibly useful from a practical perspective, because then that allows you to design your controller and check your design to make sure it is or is not guaranteed to work. Okay, so what I'm going to do is I'm going to start with the system of interconnected oscillators. And again, we're starting out with the concept that inverters will be controlled to act like oscillators. So in a sense, I'm going to be modeling my microgrid as basically a system of interconnected oscillators. So I'll be using the word oscillator or inverter interchangeably, and that's the reason why. And as I indicated earlier, anytime we see ZOSC, that's the impedance of the RLC part of the oscillator. This G of E is that piecewise linear function. Z-net is the filter impedance that interfaces each inverter output, and then we assume that there's some load here that's represented by some impedance. So this structure that we're going to look at first is just the most simple you can think of. It's just a system of parallel inverters. And I'm doing that because it turns out that from an explanatory perspective, it's a lot easier to get everyone to understand how this is working if they're looking at this simple structure rather than something that's a bit more complicated. So what we're going to do is, because we're dealing with a system with multiple oscillators, it'll be convenient to work with vectors and matrices. So this vector I is just a vector of all the output currents from the inverters. This vector V is the vector of all the output voltages of the inverters. G of E is just a vector of all the nonlinear functions, and I, SRC, is what's coming out of the nonlinear element. And then what we're going to do is take everything that has the network coupling and just represent it as a transfer matrix. So this is an admittance matrix. And so what you can do is you can relate the output currents and voltages of the oscillators, or the output currents to the voltages using the admittance matrix. So then what we're going to do is we're going to rearrange the equations to solve for V. So all we basically do is do KCL on one of these oscillators. And then once you do Kirchhoff's current law there, you just write it in vector form. And then once you have everything written in vectors and matrices, you just solve for V. It's actually quite simple. Now what we did in solving for V in this way is what we related the output voltage vector as being equal to some matrix times the vector of the currents that are leading in on here. And so this matrix relationship, so this I plus Z oscillator or Y inverts the oscillator, is a bit cumbersome to write out. So what I'm going to do from here forward is just denote it with the symbol F. So that's something we call a linear fractional transformation. And as you can see, it's a function of two different matrices, which are shown here. And one of the reasons for writing it out in this in this form where we have V is equal to a matrix times the nonlinear currents is that we can actually rewrite or re-represent the system as having a linear portion and a nonlinear portion. And it looks like a nice closed loop diagram. So again, here the voltage is V, is just a linear fractional transformation times the nonlinear currents, and then this is the vector of the nonlinear functions, or those piecewise nonlinear functions. Now what's convenient about this is that we've partitioned off the linear part of the system and the nonlinear part of the system. And that's convenient because there's well-defined ways to deal with linear systems and well-defined ways to deal with nonlinear systems. So by partitioning the system like that, we can analyze the system a bit easier. And also, by getting to this kind of closed loop diagram, we can start using notions of stability and things of that sort to analyze the system. So here, again, I'm illustrating that the linear portion of the system is encapsulated in that linear fractional transformation. and the nonlinear portion is encapsulated. So the whole point of starting this analysis was to try and understand why this system synchronizes. So what we're going to do is, first we need to define what we mean by synchronization. So here what we mean by synchronization is that the output voltages of all the inverters will be the same. So they will be oscillating together in unison. And so this definition, this is going to be the definition for what we like for synchronization. So then what we do is we utilize something called the projector matrix, which is just an n by n matrix where n is the number of oscillators in the system. And anytime we multiply a vector by the projector matrix, we're going to go ahead and just call it a differential vector and denote the resulting differential vector as u tilde. And the reason we call it a differential vector is that if you take a differential vector and you take the Euclidean norm of that vector, so for instance on the bottom, I'm taking the Euclidean norm of the differential voltage vector, you can actually show that the Euclidean norm is equal to the sum of the voltage differences squared. So this expression here for the norm of the differential vector has a direct link with what we're talking about with how we define synchronization. So in other words, the differential voltage vector is 0 if and only if we attain synchronization as defined here. So again, you can think of it as these are the differences squared. So all the differences have to be 0 for this Euclidean norm to be 0. And the reason this is useful is because if we go back to the original system that we had from a couple of slides ago, and we just take all of the dynamics for the system and multiply everything by the projector matrix, and just carry that through with the math, and we'll get to a system that I call a differential system. So again, this differential system is again just doing what we did a couple slides back, but multiplying all the vectors times the projector matrix. And you can show that the linear portion of the system, the linear fractional transformation, is the same between the two of them. But now, instead of dealing with just the vector voltages and nonlinear currents, we have the differential vector voltages and the differential vector of nonlinear currents. And because we want to look at synchronization, you can actually show that if the differential system, if the closed loop system is stable, then that means that these differential vectors also decay to 0. And if these differential vectors decay to 0, then that means that we have synchronization in the original system. So again, just to say it one more time, because it's a fairly abstract concept, we start with the original dynamics and we go to this differential system. And if we prove stability in a differential system, it implies synchronization in the original system. And then this here is just showing the mathematical condition that we need to satisfy to guarantee that the system of inverters will synchronize. So again, Z net and Z oscillator are the filter impedance of the output of the inverter and the RLC part of the oscillator, respectively. This sigma is the slope of that piecewise nonlinear function. And as long as the product of these two things is less than 1, that means the differential system is stable, which means that these approach 0, hence we get synchronization in the original system. So the proof behind this is actually based on something called the small gain theorem, which says that if you have a closed loop system like this, that one way to prove stability in it, and this is generalized to nonlinear systems like we have, you can show that if the system is finite gain L2 stable, then these signals will decay to 0. Intuitively, what that means is that if you multiply the maximum possible amplification around the loop and show that it's less than 1, then the system is stable. So then again, remember I said that we're separating the linear and nonlinear parts of the system to deal with them independently. So the linear portion, we can show that the maximum amplification by this matrix here of the linear part of the system is actually given by the peak amplitude of this transfer function. And then the maximum amplification of signal differences of this nonlinear part is just given by the slope of that piecewise linear function. And there's some really neat physical intuition that you can get out of this, because if you look at the maximum possible amplification of the linear part, it turns out that this is actually just the parallel impedance of the filter impedance given by Z-net and the RLC part of the oscillator. So there's this kind of neat physical link that comes about there. And so that's the main result for guaranteeing synchronization. So that means that from a design perspective, when we're designing hardware and we arrive at a set of control parameters, we can check whether or not the system is guaranteed to synchronize. So this here is a picture of a really small 3 inverter setup at Belltop Wells at Illinois, and it's what the experimental results were obtained on. So again, this next part of the talk is to show that you can actually apply this on a real system. So these are 3 inverters. L-net is just the inductive filter at the output. R-net is a small parasitic resistance. And then on the subsequent slides, I color code things to match the oscilloscope screenshot. So these colors for these 3 currents and the load voltage will be matching the experimental results later. And so we designed the system to oscillate at 60 hertz, and there were some rating limitations I had on the equipment, so we just designed it at a 60 volt amplitude. But it turns out you can generalize this for any sort of voltage level. And then we designed the control parameters to meet that synchronization condition that we derived. So we have a level of guarantee that the system will work. Now in this, some of this recent work that I've cited here, we've also been able to extend some of these ideas a bit. So initially, if you were observing, I was assuming that all of the oscillators / inverters were the exact same, meaning they all had the same exact power rating. But in a real system, you might have, let's say, inverter 3 might be only half the size of inverters 1 and 2. So we've also been able to show that you can get proportional power sharing by scaling some of the values in those virtual oscillator circuits. So, and that's entirely done without communication. You just have to design your controller with these scaling values to give you proportional sharing. And then also, we've been able to show that this load can be both linear or nonlinear, and it doesn't affect the synchronization condition. So this synchronization condition actually applies for non-uniform sharing or with nonlinear loads. And it should be pointed out that the synchronization condition doesn't depend on n. So you can just design one of these and check the synchronization condition. And then if it works, you can connect as many of them as you want, even at different power ratings. So this first set of results shows a system with a resistive load, and this has what I'm calling 2-2-1 power sharing. So that means that inverters 1 and 2 provide twice as much power as inverter number 3. So you can see on the top right waveform, and these are all measured, you can see that the output currents are not synchronized initially. They interact with each other, and then they do converge to synchronization after a small number of cycles. And once they achieve synchronization, you can see that we're getting that level of power sharing that we wanted. So converter number 3 is only providing half as much current as the other 2. And then we want to look at the transient behavior of the system too. So you can see here that if we rapidly step the load down so that the current it's consuming drops almost instantaneously, then the inverters will also do the same thing. And you can see that the load voltage is pretty much undisturbed in these measurements. And same thing with the load step up, they all instantaneously step up the currents they're providing. And you can see that the 2-to-1 ratio of current provided by the 3 units is still maintained in all of these. So this is a set of results with a nonlinear load. So again, We get synchronization, but what's really interesting more so about this set of slides is we wanted to look at how the system behaves as you're changing the number of inverters in the system. So let's say you remove one and then add one back in. So it turns out that inverter removal is extremely easy. You don't need to do any sort of planning for this. So for instance, if I had inverter 3, which is hiding behind you, and I just rapidly disconnect it from the system, the other two will instantaneously ramp up the amount of current such that the voltage doesn't collapse on the system. And again, it does this entirely by how they interact with each other. So they're not being commanded to do this. Now, whenever you're adding an inverter into a system, you have to be a bit careful. So what we had to do is we had to come up with a method of pre-synchronizing the additional inverter before you energize it and actually turn it on. So what that means is that let's say inverters 1 and 2 are running as I'm showing here in this experimental result. What's happening meanwhile is inverter number 3 is going to be sitting there measuring its output voltage. And there will be some sort of pre-synchronization routine where it locks onto that voltage. And then when it does, you can energize the system. And so here you get this kind of gentle unit addition. I mean, the theorem states that you can add inverter number 3 and it will be guaranteed to synchronize. That's what the math says, and it's true. But you don't want to damage your hardware, so that's the whole point of doing this kind of gentle pre-synchronization, so that you have a gentle unit addition and you're not hurting the inverters in any sort of way. The last set of experimental results I wanted to show is with an RLC load. Because the question comes up that people say is, well, you have this resonant circuit inside of your controller. Isn't some sort of RLC resonant circuit load, isn't that going to mess with your controller or mess things up? Well, our results have shown that it really doesn't matter. So on the bottom left here, this is showing a load step down. Now what's I think most interesting about this is I added these dashed lines so that you can see the change in power factor. So initially when we have the RLC load, which is the first half of this experimental result, the load is consuming basically unity power factor. So you can see that the voltage waveforms and the current waveforms are basically in phase. So the peaks and the lows line up pretty well. But if we remove that capacitor, then this load is consuming quite a bit of reactive power. And so you can see here that there is a phase shift now between the measured currents and voltages. So you can actually see that in the measurement. It does it basically instantaneously. And all of these transients where I have load steps ups and downs, they happen right at the midpoint. Oscilloscope screenshot. And then here we have the load step up, which is just in the reverse direction. So I've been, just fascinated by this topic. So, I graduated, and rather than being a PhD student who's tired of their dissertation research and doesn't want to do it anymore, I was still staying up at nights thinking about this. And so we've been trying to tackle some other open questions. So one of the questions that comes up is, people say is, well, you have idealized DC inputs on your system. Whatever power you pull out of them is automatically supplied by what is connected at the inverter. Well, in a real system with photovoltaics, for instance, maybe one of these inverters is going to have, its power is going to be fluctuating with the irradiance. So what we needed to do is we needed to figure out how to control or modulate how much power is coming out of one of these inverters with our controller. So what we figured out is there's a way to modulate one of the parameters of the virtual oscillator so that we can control how much power is actually coming out of it. And so I did some simulation work showing that if you have a bunch of inverters in a microgrid, some of them have storage and maybe some of them have intermittent renewables, that as the renewables fluctuate up and down, the storage will provide and absorb power as needed. And again, this is done entirely without communication. It's just how the system interacts, which makes it really interesting. So even then, at this point, there's still some question as to why that is happening. And we also were able to reformulate the controller a little bit so that we saw that same oscillator, but we were able to generate a set of three-phase signals coming out of this three-phase systems. Another thing that comes up too is, my initial work was assuming that everything was connected directly in parallel. So then what happens if you have, really large-scale networks that are maybe don't have this nice periodic structure, maybe it's a mesh network even. Well, what we did is we were able to extend this into look at more arbitrary network type settings. And so here's an example of a system where you have maybe all sorts of different impedances that connect these nodes. The only assumption we make in this analysis is that every line that's in the system has the same impedance per unit length. And that the impedance of the entire line is equal to that impedance per unit length times its length, which is expressed here. So Y series is the impedance of the length, and L is the length of that line, separating elements J and K. And it turns out that if you look at this type of structure, for instance, you can get a very similar type of synchronization condition as before. But we just start getting this lambda J, which corresponds to the eigenvalues for the underlying Laplacian. So it turns out that graph theory actually ties very nicely into studying these types of problems. So I guess just overall, I hope I've been able to convey that this was, at least for me personally, this was a really fascinating topic, a nice way to tie in together power electronics, nonlinear dynamics, graph theory, all sorts of things. And so it's been my pleasure to share this with you.
Plenty of time for questions.
A couple of questions. First of all, you said that synchronization happens within a few cycles. Is this dependent upon, your example was for 3 oscillators. Would this be slower if you had a large number of oscillators, or is that not?
From what I've seen, it does actually, the time it does take to converge to synchronization does depend on the number of inverters in the system. So you can imagine that if you have 100 of these sloshing around and they're not synchronized, there will be some amount of time before they do synchronize. And it will take longer than if there was just 2 or 3.
I mean, there's a certain time delay in the system also if you spread over a geographic
Right,
area.
yeah, absolutely. So if you have more impedance in the lines that's separating them, the system is larger, there's more of them, then there will be a longer time scale before you reach synchronization. So yeah, that's true.
And then finally, your nonlinear element, current source that is controlled voltage, you use piecewise linear for that. Since this is a virtual source, so you can use anything.
Yeah, you can program to do whatever you want.
Is there a reason to, besides mathematical programming simplicity, to have that, if you had a smoother function, let's say as you might get in a real negative resistance diode or something?
Right,
That
yeah.
be an advantage?
Yeah,
or
actually.
Disadvantage, or doesn't matter?
So here's a little bit of the backstory with that. So it turns out that the oscillator that most closely ties with the oscillator structure that we use is called the Vanderpool oscillator, which is probably exactly what you're hinting at. And so the Vanderpool oscillator,
It's the cubic idea.
it has this shape instead of my piecewise linear kind of approximation for it. Well, the advantages of using that is just the fact that Vanderpool oscillators have been studied for ages, and so there's a fair bit of closed form analytical expressions to maybe describe the amplitude and frequency of the system. But it turns out that from the background literature that the people have been using to study coupled Vanderpool's is in biological systems. And in the networks that people in biology are looking at, they're looking at resistive coupling. And in a power system, we're looking at inductive coupling predominantly. So it turns out that looking at coupling or synchronization in a network, where the network is not purely resistive, it actually has storage elements like inductors and capacitors, is quite a tough problem, and it hasn't been solved until just recently. So one of my collaborators who I indicated at the beginning, Abdullah Hamadeh, he was able to look at synchronization networks with storage elements. And the mathematical analysis is that he needs this nonlinearity to have a bounded slope.
What?
A bounded slope. Yeah, and as you can see, the cubic function, its slope approaches infinity as v goes to infinity. So,
Okay, so there's that kind of asymptotic.
yeah, I mean, so basically
but the sharp turn in slope versus smooth change at the peak and valley there, that doesn't seem to be a...
yeah, and actually they behave remarkably similar. So I guess maybe the short answer to your question is that from a practical standpoint, there is very little reason to settle with the piecewise linear versus this cubic.
Mainly this asymptotic behavior.
Yeah, or it's mainly because the mathematical analysis has this restriction that we need that bounded slope on the piecewise.
So when you had that stability condition, that involved the slope of this curve.
Right.
And that came from the large voltage parts of...
Yeah. So we were wanting to prove that that system based on differences was globally stable.
Okay, so it didn't come from the local slope, it came from the...
Yeah, so
Okay.
over all voltages, it has a bounded slope. Yeah.
So I think your definition of synchronization implied that the voltages are all in phase.
Right.
Is that right?
Yep.
But I would expect that the system that's synchronized would have some phase shifts.
Right, yeah, actually, so that's true. So we are working with a bit of a restricted definition of synchronization. That's absolutely true. Because in a power system, even though everything is swinging at the same frequency together, there's different power flows on different lines, so there will naturally be these phase differences between everything. And so what that means is that a more meaningful definition of synchronization will be looking at frequency synchronization. They all oscillate at the same frequency, but possibly different amplitudes and phase angles.
Could you intentionally make the phases different?
Well, in conventional inverter controls, people do control the phases of inverters to control how much power is coming out of
So
them.
not specially to this thing, but just independently.
Yeah, just in general with a power system with some sort of arbitrary network where each unit is providing different amounts of power, there will naturally be different phase angles. So what we're doing is we're actually I'm working with Florian actually, because he's done a lot of work on phase coupled oscillators where you model the oscillators as having, basically it's rotating with theta, and he has done previous work where he tries to determine what is the conditions needed so that they all oscillate at the same frequency, but possibly different angles and amplitudes. But what we need to do is we need to find a way to look at our system in a different way to reveal the underlying phase dynamics.
So your last slide had...
Yeah, so even here...
Is that with the same definition? Or?
Yeah, so even here, I think this paper, we've taken the restricted definition as far as we can go. And so we've kind of reached the end of the line, and we need to start looking at phase coupled dynamics so that we have something that's more representative of real power systems. I'll hear what you do.
So on one of your first slides, you mentioned that conventionally you use droop control in order to increase the power output of conventional generators to bring the frequency down to, or at least stabilize the frequency. And you said that that has slow dynamics and it's computational burden. I'm curious why.
Yeah, I guess it's all about it. Because if you say something's computationally intensive, it can be argued that it has to be relative to what. So what I mainly was trying to get at when I was mentioning that statement is that if you look at our oscillator, it's extremely simple. So it's basically just the second order differential equation, which means it's extremely simple to program into your controller. Now, if you're doing droop control in, let's say, a single phase or even a three-phase system, then the number of state equations starts to pile up because you have low pass filters, oftentimes just both the current controller and the voltage controller, which are managing the sinusoidal outputs. And so as you start adding up the state equations, those types of controllers can have a lot more complexity than this.
Just to comment, a simple analog system to look at some of these is a tone diameter-driven system.
Yeah.
It has a good approximation to a cubic equation.
Right, right.
With a negative resistance, and so it's a nice easy way to put things together on a small scale.
Right, right, yep. Yeah, actually, a lot of the analysis that this originates from is from the work by Vanderpool in the 20s and 30s, way long ago, when he was analyzing vacuum tubes, and he noticed there was this persistent oscillation, and it was due to the fact that the vacuum tube was acting like a nonlinear element. It had this cubic type of waveform. So, yeah, actually.
Well, the old book that I saw on this is by Hedson on vacuum tubes, and that turns out to have a very nice description of negative
Right, yeah.
resistance oscillation.
Yeah, absolutely. There's a really nice history to all this, and it ties together very well. Yep.
Maybe I missed this, but can you use this technique to synchronize the grid in reconnected mode?
Yeah, so that's another big open question that we're still working on at the moment. One of the things that the droop control has that's really nice is that droop control can work in both grid connected mode and islanded mode while using the same exact controller. You don't need to have a hard switch of mode A and mode B, for instance. So we're actively working on seeing if we can solve that problem and still use this same nonlinear circuit and synchronize to the grid connected mode. So yeah, actually that's something we're still working on.
I kind of have a related question. If you, rather than consider one microgrid and then the grid, if you can imagine a microgrid being, the grid being a network of microgrids, could you operate each microgrid as its own oscillator, and those all synchronize to each other, and you have like layered oscillators?
Yeah, so I think what you're getting at is can you kind of start scaling this up to a much larger nested structure? Is that kind of what you're getting at? Yeah, I mean, that's an interesting concept too. I think so far at this point, we've been looking at inverters that are in a fairly close vicinity. As we're moving forward, we're trying to get into some of these system considerations. And I've had that idea floating around, and so yeah, it might be a really neat approach. Yeah.
So that includes a nonlinear element. Will it introduce harmonic distortion?
Yeah, actually, so for instance, if you look at the pure harmonic oscillator, which is an LC, that gives you a perfect sinusoid. But given the fact that we have this nonlinear element, it actually does introduce some small amounts of harmonics into the system. So one way to look at this is people often call these weakly nonlinear oscillators, because if you can tune the parameters of the oscillator such that there is a relationship so that if some of these approach zero, then you recover the original perfect LC tank. And so one way to think about the problem is you want to minimize the amount of harmonics while also having the properties that we so desire. And so, yeah, actually, in our experience, the harmonics that are induced by it are really small, but we're still trying to characterize just how much harmonic content there is.
Great. Let's thank the speaker again.